Hi. First of all, I just want to apologize. I'm kind of sick today, so I don't know how long my voice is going to hold out, and I don't know, how well it's going to go, but I'll do the best I can. Okay. This week we're going to be talking about memory management. But before we do that, I want to go over a couple course policy reminders. The first one is that late assignments are not accepted after anybody has received their grade or the solution has been presented in class. Okay, so if we're already into Wednesday and you haven't turned in your assignment, you won't get any credit for that assignment. So I just wanted to remind you of that. Another thing that I wanted to remind you of is that I usually try to answer emails within 24 hours, but the problem that I'm seeing is that some of you are waiting until Sunday to get started on your assignments, or at least to ask me about things on your assignments, and I worry about that because I'm not always able to, see your email or respond to your email in time. So I don't think it's been a problem yet, but I know you're all very busy, and I've been seeing the emails coming in about the assignments with questions later and later in the week as you get busy in all your courses. So if you could try to kind of look things over earlier in the week, and so I could clear up any misunderstandings or any confusion you may have, that would be helpful. I could tell my voice isn't quite all there. Can you hear me okay? Okay. All right, I also wanted to review the academic integrity policy again. And really the policy that the university wants us to follow is that any assignment that shows evidence of academic dishonesty, plagiarism, cheating, whatever, will get a grade of 0. Okay, so it's not just a single exercise, but the entire assignment would get a 0. And there still seems to be a little bit of confusion about this. And so I wanted to go over it again just so you're clear. The first thing is cheating. Cheating is defined as using or attempting to use unauthorized materials. Okay, so if you have a copy of the publisher's solutions and you look at them at any time during this course, you are cheating. I just want to be clear on that. Okay, I know a lot of you have the publisher's solutions or had them in the past, and I know a lot of you are only trying to improve your learning by looking at it and trying to make your answer better, or see what the publisher said the answer was. But if you look at that, you are cheating. That's as simple as it is. You're using unauthorized materials in the class. So I just want to make that perfectly clear. And I will give 0s if I suspect that you're using the publisher's solution in the class. Okay, so, and I know there are some answers that your wording is going to be the same or very similar, because there's only one right answer. But for a number of problems, there are a number of ways you can answer the question, and I just want to be clear on that. The other thing there still seems to be some confusion on is plagiarism. And again, plagiarism is submitting all or part of another's work as your own. And I think where the confusion comes in on this one is I'm still seeing people submit things where the words aren't your own words. I can find those same words in your book, on the web, or in the publisher's solution. And I think what happens is, I know a lot of you struggle some with the English, and so you memorize a lot of what you read. And I understand that, and then that may have helped you on tests and so forth in the past. But even if you memorize it and just give me those exact words back, that is plagiarism. Okay? And what you need to make sure is that you're getting a deeper understanding of the materials. And I wanted to just show you this chart. This, if you've ever taken any education courses, and I don't know what all of your backgrounds are, but there are different levels of understanding or knowledge or learning. And really the lowest level of learning is knowledge. And that's where you just memorize something and you repeat it back. Okay, that's kind of the first step in learning. You have to know what the definitions are of the different terms and so forth. But what you're really doing is just memorizing and repeating what you've memorized. What I'm looking for in this course is these higher levels of learning. I'm looking for some comprehension. I'm looking for application. I'm looking for analysis. I'm looking for synthesis. And I'm looking for evaluation. I want you to take that knowledge that you're memorizing, the things that you're memorizing from the book, and use that to, explain to me what something means, to apply what you read to a certain problem or an exercise. It's a higher level of learning than simply just repeating what you've read. Okay? And so I'm trying to kind of push you up this pyramid, push you up this triangle to get you to these higher levels of learning. And I know you have to do memorization, and I think in some cases memorization helps a great deal, especially if you're taking a multiple choice test and that type of thing. But a lot of times in your answers for your exercises and your programs, I'm looking for you usually to do things like apply what you've memorized, apply what you've learned. And if you get into doing the papers that are assigned in this class, which we talked about a little bit last week, you may even get up to the top of the pyramid here by evaluating what you've read and saying, do you agree with the results or don't agree with the results in any given paper? So that's really what I'm looking for. I'm looking for your knowledge or your learning to be in the higher levels of this pyramid rather than just the bottom level of the pyramid. And I am grading on that. And some of you have given me answers, and I've asked you additional questions about your answer, and you explain the words, but because the words came directly from another source, you're misinterpreting those words. And if you would have written it in your own words, I could have recognized that misinterpretation and help you with the pieces that you don't understand. But if it's just something that was copied, I really don't have any way of knowing how deep your knowledge goes. And that's what I'm really looking for. How deeply did you learn this material? Okay, so I don't want to, spend too much time on this. I just want to kind of let you know why I'm so vigilant about this and why I'm trying so hard to get you to move up this pyramid of learning. Okay, so let's go on and talk a little bit about the solutions for last week's homework problem. And the first problem was to identify a race condition. And we had an example of a banking system that has a deposit and a withdrawal. And you can assume that a husband and wife share the bank account, and the husband tries to do a withdrawal and the wife does a deposit. Show how a race condition is possible and what you could do to prevent the race condition from occurring. And there's lots of ways you could have shown this to me or explained it to me, but here's kind of how I looked at it. And of course, your answers were different than this, but this was my answer. I said, okay, let me assume that the husband kind of gets to the bank account first and gets the balance. Okay, even if you're doing a simple equation in a programming language, realize that equation is made up, or a simple assignment, that assignment is made up of multiple parts. First, the low-level instructions have to actually, get the balance from where it's stored in memory, put it in a register. If we're using that in a calculation, we have to get the CPU has to get the other amount, put that in a register, do register manipulation to actually do the addition, subtraction, whatever the operation is, and then store it back into memory. And so anywhere in there, there's a possibility that something can interrupt this process, especially if you're doing a multi-threaded process where you have multiple threads accessing the same data. And so what could happen here is that the husband gets the balance and subtracts 200 from the local copy of the balance that the husband has. But the balance that was stored out in memory is still 500. So when the wife does the deposit, she gets the balance first of 500. And then she adds 50 to that, her local copy of the balance, so she has 550, where the husband then stores 300 back out in memory, and then the wife goes back and stores 550 back out, which obviously is the wrong answer here. Excuse me. So you can kind of line this up any way you want to show how a race condition could possibly occur. Now, the way we talked about preventing a race condition was doing things like using semaphores or mutex locks or using monitors. All those are solutions to the race condition. And so the way I would have prevented a race condition in this case is by preventing two resources from accessing that balance concurrently. And so in each routine, both the withdraw and the deposit, I would first try to acquire a mutex lock on the balance. So the husband would try to acquire a mutex lock, and then if he was then manipulating the balance, the wife wouldn't be able to get to that balance until the mutex lock was released. So the husband would acquire the mutex lock, get the balance, subtract 200 from the balance, store the balance, and then release the mutex lock. And it wouldn't be until this point that the rest of the deposit code would continue executing. Okay? And then eventually the wife also would release the mutex lock that she acquired. All right? Is it required that we clarify the type of lock and where we use it? If you knew generally that you needed to kind of protect the critical section and you explained it that way, that was acceptable as well. Is that what you're asking, Hala? Okay, yeah. I did a very specific example. But if you talked about it in general and you had the idea right about protecting the critical section, kind of the entry into the critical section, then releasing any locks or whatever at the exit of the critical section, that's fine as well. And I will be getting your grades back to you today, I hope, if everything goes well. As I said, I'm not really feeling very well today, so we'll kind of see how it goes. Any other questions on this? Okay. There were some interesting answers for this one. This one is: consider a system consisting of 4 resources of the same type that are shared by 3 processes, each of which needs at most 2 resources. Show that the system is deadlock-free. Okay, so remember there were different conditions for a deadlock. Okay, there was the mutual exclusion, the hold and wait, the circular wait, the preemption, and so forth. For me, the easiest way to describe this was, again, to use an example. And again, some of you didn't do this. Some of you, just used kind of the general terms and explained how it would work and why you couldn't get a deadlock. But for me, the easiest thing was to create an example. And so what I did is I drew a picture where I had my 4 resources and I had my 3 processes. And I said, okay, in this example, each process needs up to 2 resources. So in order for there to be the greatest potential for a deadlock, I'm going to assume that all my processes need the maximum number of resources, which is 2. So in this example, I'm going to say P1 grabs resource 1, but before P1 can grab resource 2, P2 grabs resource 2. So P1 is waiting on resource 2 while P2 is holding resource 2. It's been allocated resource 2. And I'm also going to assume that before P2 can grab its second resource, which is resource 3, P3 grabs resource 3 and then also grabs resource 4. Okay? In this case, there would be no deadlock because resource 3 has both of the resources that it needs, and therefore it would not it would be able to execute, eventually release its resources, and then the other processes would be able to proceed. Okay? Any questions on that? But you change it to 7.8, isn't? What? I'm sorry. What is your question? I did change the assignment from 7.8 to 7.7. But if you did 7.8, that's okay. I will accept that if there was some confusion. I felt that 7.7 was a slightly easier assignment, so I changed the assignment to be 7.7 instead of 7.8. Okay, Hala says, no matter if the first process or the last holds 2 resources. That's correct, Hala. No matter how I drew this picture, no matter how they grabbed their resources, it would always come up with one of the processes being able to get 2 resources at some point. And as long as one of them can get 2 resources, then that process will be able to finish, and there will not be a deadlock because the other processes will eventually get the resources that they need. Okay, remember the circular wait is when process 1 is, or let's say process 3 is waiting for a resource that process 2 is holding, and then process 2 is waiting for a resource that process 1 is holding, and then process 1 is waiting for a resource that process 3 is holding. And no matter how I drew it, I couldn't get that situation to happen. Okay? And Amal, yes, if you did the wrong problem, if you did 7.8, that was a little bit more difficult problem, I felt, because you had to do a proof. But if you did that was okay too. Okay, I understand when I changed the assignment, you don't always catch it in time, and you've already answered the original assignment. Okay, any other questions on this? Okay, let's go on then to our week 5 learning. And in week 5, we're talking a lot about memory management. And we're going to be looking at the various ways of organizing memory, various techniques for allocating memory to a process, and then we're going to look at paging in quite a bit of detail. Oh, regarding the arrow direction, because the direction needs hold or wait. Yeah, what I was doing in mine, I just used different kinds of arrows to say whether it's holding a resource or waiting for a resource. Okay, this was just how I personally solved the problem. Does it make sense to you, Hala? Okay, yeah, they're doing kind of a hold. The process gets the resource, and a wait is when the process is waiting for a resource. And so they show it a little bit differently than I do in my example. Okay, and it's just symbolic. Okay, it's just kind of showing how it might work. And so you know, I'll understand what you're trying to show me if you showed me a diagram. But I'm really losing my voice. I'm sorry about this. Okay. Let's continue here, and I'm going to try to get through this. I'm really, I could tell I'm feeling worse as I'm trying to talk and do all this. So I'm going to try to get through it in the hour, because I don't know if I'm going to hold up much longer than that. Okay. Memory management. Remember that programs have to be retrieved from disk and placed into memory in order for them to run. And we only have so much main memory. And if I look at all the processes we could possibly be running on my system, there isn't that much memory. We can't store all the processes in memory at the same time, usually. Okay, but main memory and registers are the only things that the CPU can access directly. So we try to do as much as we can in registers, because the CPU can access registers very quickly, and so there's a whole set of registers that the CPU uses. And using main memory often takes a lot of clock cycles, and so our fastest access is to access things in registers, and then next fastest is to access it in main memory. And then if we can't access it in main memory, we have to go and get it from disk. And we'll be talking about how some of that is done. The other thing to understand with memory management is that we also have to protect memory. So we have to make sure that one process isn't using memory that actually belongs to another process. So part of what we do in memory management is we have what is called a logical address space. Processes are in memory, and we're not really giving the process, or the process really doesn't look at it as having the absolute value for the memory in the absolute value for the memory address, the physical memory address. Processes are going to be distributed throughout memory, and so what we need to do is look at where does this process start in memory, and then how big is the process? What's the limit of the amount of memory that this process has? And so associated with a process in memory is a base register and a limit. So this process here has a base register of 300,040 and a limit of 120,900. That is the only part of memory that that process can access. So the CPU is checking to see that every actual access to the physical memory is in between the base for that process and that process's limit. Okay, so that's one of the first things that the CPU has to do, is make sure that each process is only accessing its logical address space, and its logical address space is mapped to the physical address space in memory. Now, programs use, or processes use, these logical address spaces, but somehow they have to be bound to this relocatable address or the absolute address in memory. And there's three different times that we can do address binding. The compiler takes the symbolic addresses. In other words, every time you have an instruction, that instruction's actually going to be in memory somewhere at some point, and it's going to have an address in memory. And every piece of data that you use in a program is going to have an address. So we might think of a variable as an address of I, and the compiler will bind that actual address for that variable, its logical variable, to a relocatable address, saying that variable is somewhere in my program, and the compiler might create what's called a relocatable address, which means it's that variable I is so many bytes from the beginning of my program, and that's the relocatable address. The compiler also might say, okay, I'm going to generate an absolute address because I know where this program is going to be allocated in memory, so I know where the beginning part of my program is, where my program is going to start in memory. So I can say, okay, if my program starts at address X, then my variable is going to be X plus some number of bytes that the compiler knows, and it could calculate the absolute address. Usually we don't know where a compiler is going to, the compiler doesn't know where the program is going to be loaded in memory when it runs, so it creates relocatable addresses. Another time that we can calculate addresses and bind addresses is when these relocatable addresses that were generated are then bound to the absolute address. When the loader actually takes a program and loads it in memory, it now knows where that program is going to be loaded. So it can bind that relocatable address, which is really just a displacement from the beginning of the program. It now knows where the program actually is loaded in memory, and so it can add all those displacements onto the beginning address and come up with that absolute address. Now the third time, or the third place that binding can be delayed is until runtime. And most general purpose operating systems do this, because what you want to do is delay it as long as you can until you're pretty sure where all where the code is going to be loaded. And we do something called dynamic loading because what we want to do is be able to keep the code out on disk for as long as we can, load it into memory, and so it doesn't even know all the code that when a program is loaded in memory, it doesn't always know everything that it needs in order to run. You might be linked to different routines, but you may not actually use those routines. So with dynamic linking, or dynamic loading rather, we don't actually load those pieces in until we need them, and that's actually at runtime that we know when we need them, and so the addresses aren't bound until we get to the actual runtime and we actually know we need that piece of code. Okay, so we could do it at compile time, we could do it at load time, or we can do it at execution time. And when I say we, I mean the operating system. Okay, part of the way that these addresses are bound is by using what is a piece of hardware. Actually, the way the device or the address gets mapped is a device called a memory management unit, which is abbreviated MMU. And the CPU generates a logical address. Okay, it's in the logical address space, kind of where this process is in memory and where the address is of this piece of data or this instruction within that process. But at some point, that has to be mapped to the actual physical address in memory. And think a few slides back where I showed you where the processes were loaded, and we had that base register and the limit and so forth. And what we want to do is kind of take that base register, which is also called a relocation register, add the piece of the logical address, which is the displacement, and come up with the physical address in memory. So that's the job of the MMU. The MMU is this piece of hardware that actually does this mapping. So the CPU is always creating these logical addresses, but eventually it has to be mapped to the physical address. And again, I already talked about this a little bit, where we have this concept of dynamic linking and dynamic loading. And this kind of complicates it even a little bit more, because with dynamic loading, a routine isn't loaded until it's called, and then the addresses have to be actually resolved at runtime. The code is kept on disk in relocatable form, and it's loaded as needed. And this is usually done with system code that's linked to user code. So you get better memory space utilization in memory, because unused routines are never loaded. Routines are kept on disk in their relocatable format, so they just have to be brought in with that virtual address, and then they're actually the physical address is generated. And so when there's lots of code, like a lot of times your user programs are using system code, all that system code doesn't have to be in memory all the time. It only gets called in there or put in there when it's needed. Okay, so the operating system often provides libraries that'll help to do this dynamic loading, and those libraries will just reside on disk until they're needed. In some cases, they're not even linked to the user program until the program is run, and this is called dynamic linking. Usually with a compiler, they go through a process where the code gets compiled, and then the next step that you often don't see is when it gets linked, and that's when all the system function is linked in, and then finally it gets loaded when it's executed. In your Java programs, for example, you might compile your code, but it isn't until when you try to use it that it links in some of the system code and runs it. You might have noticed sometimes when you're compiling your Java code, it's also doing the linking step, and sometimes it can't find some of the Java libraries. Okay, that would happen at the linking step. That happens when you go from source code to executable code. Usually the linking happens at that time. But sometimes we dynamically link some of the code, and this again is usually these system libraries that we don't need that often, or we don't want to actually have to load or become part of our final executable program. We want to actually only link those as they're needed. And so linking is postponed until execution time, and what happens in your code is that there's just a little stub in your code that tries to locate it's actually used to locate the actual system routine. So what gets linked in is this stub, and then when you get into actually running your code, if it gets to that stub because the code hasn't been loaded, it will then load that, link and load that code, that system code, to your address space. So dynamic linking, again, is very useful for libraries, especially shared libraries like system libraries. And you might have seen things called DLLs on your system. These are dynamically linked libraries. Okay, and so that they get dynamically linked and loaded. So we could have dynamic loading, we could have dynamic linking, and we can have dynamic linking and loading. And all this is done simply to use as little memory as possible, because memory is a very fixed resource on our system. And we want to make sure that our processes can run, and we can get as many processes running as possible, or at least we want as many as we can without degrading the performance of the operating system. Because if we get too many processes in memory and it has to start swapping things in and out, then our performance is going to degrade, and we want to kind of to try to avoid that. And so that kind of brings us to our next topic, which is swapping. And what swapping does for us, it allows the total address space of all processes to be exceed the actual physical memory. Okay, so what happens is a process can be in memory, and then if another process wants to run and they both can't fit in memory at the same time, the first process will be swapped out to disk. The second process will be swapped in from disk and put into memory. And the disk is often called backing store. I think you've seen that term in your reading. But the backing store is usually a fast disk that's big enough to accommodate all the memory images for all the users on the system. And so it's a way that on disk it has a direct access to those processes. So it's a very fast read from disk, because there's faster ways to read and slower ways to read from disk. So this is a very fast way to read from disk. And what happens is that things are kind of rolled in and rolled out of memory. And this sometimes is done. We talked about priority scheduling. With priority scheduling algorithms, we saw that where we took a process that was running and we didn't allocate it. We released the CPU and we got a new process that was higher priority back in the system. And a lot of times in a system like that, when that one process, the lower priority process, is taken out of memory, it may actually be swapped out to disk. Now, part of the swap time, of course, is going to be the transfer time, and you know, that's the time it takes to swap these things in and out of disk. Now, usually you try to not swap, because no matter how fast your disk is, it's still slower than memory. So on modern PCs and servers, swapping is only done when memory allocation crosses a certain threshold. When memory, you know, is getting so full, then your system might have to start swapping in and out of memory. And you may have seen this on your system. I know my system gets into this sometimes when it seems like some of my background processes are running, my Norton antivirus starts running, and my Windows update starts running, and all this, and all of a sudden, man, my disk drive is going nuts, because there's so many things going on in memory, as well as all the things I'm running, that everything is getting swapped in and out of disk, because my antivirus is bringing things in and out of memory so that it can check it, and Windows is bringing in things in and out of memory so it can check to see if I have the latest copy, and it's checking my Word documents to make sure there's no viruses and blah, blah, blah. And all of a sudden, I'm not getting anything done in my system, because, you know, all these processes, they can only work on things when things are in memory. And so it starts swapping everything in and out. And it drives me nuts, and I usually reboot my system at that point because I can't kill the processes. So anyway, usually on PCs, we try not to swap, because it does slow your system down. Excuse me. So I have a question. Oh, I'm sorry. I have a question. Do you think tablets and cell phones use swapping? And why or why not? Do you think your cell phone does swapping? Okay, you think yes? Okay. The answer actually is no. Usually swapping is not done. I'm really losing my voice now. Usually swapping isn't done on mobile devices because you don't really have a hard drive on your mobile device. You have flash memory, and flash memory is much smaller than what you have in disk storage. Okay, so if there's not enough memory for a process, there's nowhere to swap it to. The flash memory is used, as different processes are running, but it doesn't actually swap things out of flash. Remember that swapping is really used so that it looks like your the amount of address space available for processes is much larger than the physical address space, and so things are swapped out to this slower device, and it doesn't do it on a mobile device. Okay, yeah. Usually with swapping, we're talking about a hard drive. That's correct. Okay. All right. Okay, so we know that things are going in and out of memory, and we have this virtual address space. And so I'm going to talk a little bit about how does the system decide to actually allocate memory to a process. And what usually happens is we have multiple partitions in memory. And so that means a lot of times your memory space is divided into fixed size partitions, and processes are loaded into those free partitions. So a partition is a certain number of blocks in memory, and when a process is ready to be run, it's simply loaded into a partition, and then it runs. So if we have 5 partitions, we could have 5 processes loaded. Okay. Another thing that happens is that instead of having fixed size partitions, we have what are called variable partitions. Hala asked, are we talking about it at the same time? Yes, with multiple partition memory. Remember the first picture I showed you, where we had the operating system in memory, and then we had a process, and then we had a process, and then we had another process, and then we had some free space. You could assume that's kind of what memory would look like with multiple partitions, where each partition is a fixed size of memory, and we simply load a process into that fixed size. So you want your partitions to be big enough so that the entire process can fit into that partition. And there may be space left over in that partition. Okay? Now, it's kind of hard then to decide how big should these partitions be. So fixed size partitions was something that was done, long ago, back in the 60s and 70s. And now more things do more of a variable partition scheme. And this is also called dynamic storage allocation. And with a variable partition scheme, the operating system keeps track of what parts of memory are available and what parts are being used. And so what it tries to do is it actually tries to fit a process into one of these holes in memory. So the parts of memory that are available, they call a hole. And so if you think about it, if you can conceptualize this, there are processes all over in memory, and in between the different processes, there are pieces of memory that aren't used. And so when a process comes ready to be executed, it's going to try to fit that process in one of those holes. And there are different algorithms that are used to try to fit the processes into the holes that are available. One strategy that might be used is called a first fit. First fit, it tries to put the process into the first hole that's big enough. So it'll start looking through memory, and as soon as it finds a hole that's big enough, or it'll start looking through its partition table, and where it finds a hole that's big enough, it'll stick it in the first hole it finds that's big enough for that process. Another scheme that might be used is the best fit scheme. In the best fit scheme, it tries to find the smallest hole that's still big enough for the process. So rather than using the first one it finds, it looks at all of them and says, which one is closest to the size of this process, but I can still fit the whole process in here. And that's the best fit scheme. It tries to find the smallest hole in memory that's big enough. And then there's also the worst fit scheme. In the worst fit scheme, it looks and finds the largest hole available and then puts the process in there. Now, what do you think would be the advantages of these different schemes? What do you think an advantage is of the first fit scheme? Any ideas? Okay, Hala has a question. Depending on what the operating system decides which one must be used, I'm not quite understanding your question, Hala. Are you asking what which scheme does a particular operating system use? It's simply a matter of, when the operating system was implemented, the operating system developers would pick a scheme to use, and there's all these algorithms. Okay, Amal says one of the advantages of first fit is organizing the data. You're on the right track here. Think of what the operating system's doing here when it's trying to find a hole. In the first fit scheme, it may find in the first fit scheme compared to the best fit and worst fit, it's picking the first one where there's enough space, and that's correct, Hala. Yep, it's actually finding the first one. So there might be lots of holes in memory, and as soon as it finds one that's going to work, it sticks the process in there. Now there might be a better fit later on, okay, but first fit actually is the fastest. So that is one of the advantages of first fit. What's one of the advantages of best fit, do you think? Okay, remember it's looking for these holes, and it's trying to use memory as best it can. It's trying to use memory the most efficient way. So with a best fit, what's going to happen? You're going to possibly manage the memory better, like Hala says, because what you're going to end up with in best fit is only have a very small leftover space. Okay, it's going to take longer with best fit though, because you have to look through all your holes to find the one that fits best. Okay, so Amal, the timing is important. This isn't as good as first fit for the timing, but it's better than first fit in terms of the amount of wasted space for that particular hole. Okay, because what you have left over after you allocate the space for this process is just a little teeny tiny, piece of memory. And then worst fit, you might say, well, why would you ever use worst fit? Why would you want to allocate, the biggest hole? Okay? Remember that the leftover space can be used for something else, can be used for another process. Okay? It could be dynamically allocated to another process. So Fatima is right. For the worst fit, you not only are using the largest hole, which would be the worst fit, you also have the largest leftover amount of space, which gives you a better possibility of actually having enough storage, or enough memory, I should say, for another process to be loaded. Okay, so they all have their advantages and disadvantages. Usually, first fit and best fit are better in terms of speed and storage utilization. Okay, first fit is fast. Best fit uses the storage more efficiently. But both first fit and best fit, these are hard to say fast, both first fit and best fit have a problem of fragmentation. Worst fit doesn't have the problem because you always have this big chunk of memory left over, and so you don't run into a fragmentation problem. But with first fit and best fit, you end up with these little leftover holes scattered throughout memory. So there's really two types of fragmentation. Internal fragmentation is when physical memory is divided into fixed size blocks, and the blocks are allocated to a process, and you get little holes inside a partition. Okay, so there's space inside a partition. And remember, you're just putting one process into a partition. And with external fragmentation, what you end up with is, remember, we can dynamically load these processes and dynamically allocate space, but we still end up with these little pieces of memory where they're too small to load anything. And so what we end up having to do is compact our memory. Okay, and compaction, if you think about it, you might have had to do this on your hard drive. I don't know if you've ever had to compact your hard drive, but backing store has the same fragmentation problem as main memory, where you keep putting files and things out on your disk drive, and then if you look at a map of your disk drive, you can see that there's tons of little tiny spaces and not much big chunks of free space. So you have to defrag. So you can defrag your hard drive to give you more hard drive space. You can compact your memory to give you more memory space. But compaction can only be done if the relocation is dynamic and it's done at load time. Because remember here, we're still talking about being able to load a whole processing into memory at a time. So they've come up with some schemes to solve the problems that just partitioning has, and that's where we get into segmentation and paging. And segmentation is pretty easy to understand. What we want to do is be able to kind of break our program up into smaller pieces, so we don't have to load the entire thing into one big chunk of memory. Okay, so if you think about it, what we've been talking about up to now is having a program, and in our program we have variables, we have classes, we have methods, we have things that it's linked to, Java libraries and so forth. And in the other schemes that we've talked about, we were always assuming that the whole process had to be loaded in one contiguous space of memory. In other words, all of it had to be loaded in memory with no gaps. Segmentation takes the idea in saying, okay, what if I broke my program up and I had different segments, and I could load these different segments into memory, And then I use something called a segment table, which is how I would find where each segment was in physical memory. Oops, my little hand is falling off the page. Okay, so segmentation is a solution where every segment has an identifier and a length. Okay, and that's listed here, the identifier and a length. And the identifier here is kind of the segment number, which is an index into this table. And it has the length, that's the limit. And we know where each segment starts now. And so it can calculate where it is in memory. So we've kind of solved part of the problem of needing to allocate contiguous space for a process. But that still doesn't solve our whole problem. We have to take it a step further. And we take it a step further by using paging. I know it's getting close to our end time, but as other weeks, I am going to just continue through this. Will segmentation affect the time of processing? Yes, this will affect the time of process, the time it takes to process, because it actually has to do this extra little calculation to find these different segments in memory. Let me go back a page here. That's a very good point, Hala. There is some time that's used with segmentation because, for instance, if we're in a routine in segment 0 and then we hit a function that's doing a square root, it has to look up the square root where that segment is in our segment table so that it can find that segment in memory. Okay, so there is a time, it takes a little more time, but there's a trade-off here. You get more processes loaded into memory. So maybe this one process or all the processes may take a little more time to do segmentation, but they end up in the long run waiting a lot less time because we're not waiting for these big pieces of memory to become available. Okay, do you see, Hala? That's kind of the trade-off. There's a little bit of a time hit to go through this, but it's not nearly as bad as having to have the whole process in a single contiguous memory space, because we usually don't have memory spaces that are that big. Okay, so while paging solves the problem of needing contiguous memory space, it doesn't solve the problem of fragmentation. Okay, still when we're loading these things in memory, there's going to be these gaps. And so what we do now in most operating systems today is we do something called paging. And we have pages which are a fixed size block in logical memory. And those blocks of logical memory get mapped to the physical memory. Okay, so a page table is going to map the logical address in a program to a physical address. Paging also allows you to indicate whether a valid page is being accessed because the part of what the operating system has to do is make sure that different processes are only accessing pieces of memory, in this case pages, that they're allowed to access. And so we're kind of breaking things down even farther into these pages. And what we want to do is actually usually use a combination of segmentation and paging in most operating systems today. And again, if you have to leave, that's perfectly fine. Just leave, and I'll just continue on, and you can just listen to the recording when we're done. Okay, so now the CPU is going to be looking at addresses, And those addresses are now going to be a page number, which is an index into a page table, and an offset. And so what we're doing now is we're actually coming up with a scheme that allows us to have more logical memory than we have physical memory. And these pages can be broken up so that they fit very well with our external pages, or I should say our external memory, or our physical memory, I should say. We have let me restate that because I confused myself here. We have a logical address and we want to map it to a physical address. And so we break our logical addresses up into pages, and then we can map the page numbers and the offset into those pages to our physical memory. Okay, and that's what we want to do with the paging, and we can work with our pages so that there's a better match, and so that we don't have all this fragmentation going on, because now we're looking at pages in memory that are being allocated, and we can match them up kind of more easily because we're doing this paging. So now when the CPU has a logical address, okay, we're no longer trying to map that directly into physical memory. It's going to actually be mapped to a page, which is then mapped to the physical memory. So now a logical address is usually like a 32-bit address, and part of it is the page number, and part of it is the page offset. And actually the program that you're doing in this week's assignment is looking at exactly this. It is giving you an address and saying, what is the page number for this, and what is the offset? So you end up with a logical address space that's 2 to the m power, and a page size that's 2 to the n power. So kind of this part of the address is the offset into the page, and this part is the page number. Okay, so we have these two pieces of a logical address, and you can go through and structure your page table so that you have these 32-bit logical addresses with a page size of 4K. And if you have 4K blocks in memory, you can easily map your logical page sizes to your physical pages. But you would need to map all the address space. If you have a page size of 4K, you would need over 1 million entries in your page table. Okay, so let me just go back a slide here. Your page table is really these logical addresses, and I should have put a picture of the page table in here, but basically your page table is a page number and an offset. And the page number and the offset gives you a mapping into your physical page, okay, in memory. So what you end up with is your logical address, which is your page number and your offset, gets mapped to a frame, what they call a frame in physical memory. And I thought I had a slide in here that illustrated it, but I seem to be missing that. I don't think it's in here. Anyway, it is in your book where you can see this mapping. So we're mapping a page number with a page offset to a physical frame in memory, which will then just take you to that location in your physical memory. Okay, but the problem is that all these addresses that we need to map, this logical address space, can get very big. So if with a 32-bit logical address, we'd need 1 million entries in our page table, And if each entry in our page table, like I showed, is 32 bits, 4 bytes, you need 4 meg just for your page table, just to hold that one little thing that your operating system needs in order to manage your memory. So they came up with a little more difficult scheme, or a little more complex scheme, where you have still your page number and your offset, but now we're going to have pages of pages. In this technique, because our page table can get so large, remember now here's kind of what your page table would look like. Here's a single page table where you have a page number and an offset, and that points you to the correct place in your physical memory. Okay, so your page number and your offset is pointing you somewhere in physical memory. So we really just have this. That's what a simple page table looks like. I said I didn't have a slide, but it's kind of on this slide anyway. But our page table can get so big, this can be 4 megabytes of memory just in itself. So what we do sometimes is we have a hierarchical paging scheme where we have page tables of page tables. Okay, and you don't have this in your homework. We're doing a simple page table in our homework, but it can get more complicated where our page number now has part of the address now rather is going to be an index into our outer page table. The second part of our page number is the index into our inner page table, and then the third piece of the address is an index into our actual memory, or our offset into our actual memory. Okay, and this is just a 2-level hierarchy. If we had a 64-bit memory space, we might have a page table of a page table of a page table. Okay, and it can get very, very complicated. But what we're really trying to do is be able to get from our logical address to our physical address as quickly as we can. Okay, so our book talks a little bit about, what we have with just a single page table, and that's what your homework assignment talks about, but realize that this can get more complicated by having a hierarchical page table. Another way we get away from this limitation of having these huge page tables is, again, with a single page table, we pretty much have a page table that has your logical addresses, which are your page number and your offset into the page. But our page tables are getting too big to just store all those in a simple page table, so we could potentially come up with what's called, or use what's called a hashed page table. And this is common in address spaces where your logical address is greater than 32 bits. Okay, and that's where if we were using the hierarchical page tables that we were talking about, you might have a page table of a page table of a page table and so on. So here, the logical address is really a virtual address that's been hashed. This logical address gets hashed by a hash function, and it gets stored in what's called a hash table. Okay? Now, the hash table then is a data structure, and if you're familiar with hash maps and so forth, that data structure, when it hashes this logical address, the page gets hashed to an entry in the hash table, and then that hash table points to a queue of all the different possible pages that that are in memory that all hash to that same hash function. Okay, remember, a hash function doesn't always give you a unique address or a unique value, so you can have this queue of pages based on that same logical address, or on different logical addresses. They can be hashed to the same entry in the hash table. And then we have a queue that actually, they'd go through this linked list to find the actual page and then map that to the physical address. So each element in our hash table contains a queue or a linked list, and each element of the linked list contains the virtual page number and then the value of the actual frame, and then it has the pointer to the next address that would have been mapped to that same hash value. Okay? So again, this is a little bit larger or a little bit longer process to find this physical address. What this really gives us is the relocation register. We still have to add the displacement or to it, or the offset to it, and so there's a whole thing that this you have to go through to go from this logical address to the physical address. We have to go to the hash function. The value from the hash function gives us this linked list. We have to search the linked list, which finally gives us what frame in memory, and then we add the offset, and then we get to our physical memory. Okay, again, this is taking some time, but the advantage is, again, we're not using as much memory for our page table. Okay, so it gets complicated in terms of the algorithm, but we're trying to conserve memory, not processing power. Doing a hash function is pretty fast. Doing table lookups are fairly fast, and so forth. We're trying to maximize how well we use or the utilization of our physical memory, and that's what we're doing by coming up with ways of making our page tables smaller when we have huge address spaces. And then there's also a physical or an inverted not hash table, an inverted page table. Let me get the words right. It's an inverted page table. And here, again, we have this where we have our CPU generating our logical address, but the logical address actually includes the process ID and then our page and offset. Okay, and what we want to do here is actually find the process, because the process, when we find that process, it's going to give us a pointer, an index actually, into our page table. Think about an array. If you're searching through an array to find something, once you find it, you know what index it is in that array. And that's what we're really looking for. That index in this array is actually the physical page number. This I that you see here, this is actually the frame number that's used in the physical address space. So really now our page table, instead of being a list of all the where all the logical pages are in memory, we've kind of inverted the process. We actually have an entry, instead of for each page, we have an entry for each frame. We have an entry for each frame in physical memory. So as soon as we find where this page is located, we now know what frame it's in, and we can just, again, add the offset. So now there's only one entry in our page table for each page of real memory, for the physical memory. And so our logical address space could be very big, but our page table is never going to have more entries in it than we have actual physical frames in memory. So the index at which the process ID and page number is found is really just the number of the frame in physical memory. So that's what makes sure that our inverted page table will never have more entries than the number of physical pages in memory. And there I'm talking about the physical memory. So it gets a little confusing because we're talking about these logical addresses, and in this case, the logical address has the process ID and the page number. It has to search for that process ID and page number to find where the physical page is in memory. When it finds the physical page number, it then can add the offset and get into our physical memory. So again, this is just another way that we're trying to keep this page table small, and here we're doing it by saying we're only going to put things in our page table if there is a physical frame that matches it. And so if the CPU gets a logical address, looks for that page number and process ID in the page table and doesn't find it, it now knows that that address that it's looking for is not in physical memory right now. And then it has to either get it in memory or figure out what to do. Okay, so all these, very, complex things, or at least it seems to us as complex because we're not used to thinking about all this kind of stuff is going on all the time, just so it can manage the memory that it has. Okay, any questions on that? Your book goes into a lot of detail on it, but basically what we're trying to do is just minimize the amount of memory that's used to manage memory is what we're really trying to do here. And before I go on, just remember that most operating systems use segmentation. They use paging so that you don't need to have big pieces of contiguous space, and then it uses some paging scheme to try to minimize the amount of free space in memory so that we can fit as many processes in memory as we can. Okay, so that's kind of everything that memory management is about. Okay, and there's even more to it, which we'll get to in Chapter 9. Excuse me. So your first question for your homework is consider a computer system with a 32-bit logical address and a 4K page size. And we kind of looked at that, and we said, that means that part of it's going to be used for the page number, the other part of it is going to be used for the offset. Okay? Assume that the system supports up to 512 meg of physical memory. How many entries will there be in the page table if we're using a conventional single-level page table? Okay, so there we're kind of looking at the case that you're also looking at in your programming problem to say, if we have a 32-bit address, logical address, what will our addresses look like? And remember that your address is split into the page number and the offset. And so that's really what we're looking at here, is just that page number and that offset to say, okay, how many entries do we need now in our page table to map this physical memory space? Okay, so I want you to explain your answers. And this one's pretty easy because we can actually, there's nothing fancy going on here. We can actually look at how many bits are being used for the offset and how many bits are being used for the page number. And the page number is what's being stored in this page table. So how many page numbers can we possibly have? And that's kind of what this question is asking. And then you want to look at an inverted page table. And here, what's important is knowing that we have 512 meg of memory, and that's divided into 4K pages. And so how many entries will there be in the page table? And remember, I said in inverted page table, we have one entry for each frame in physical memory. And so these are fairly simple calculations that you can do to answer these questions. But don't just give me the number. Give me the explanation. Why did you do that calculation? What is the calculation that you did to come up with that number? Okay, and it is fairly simple once you understand the terminology. The next assignment rather that you had is another one about paging, because that's what it's all about in memory management and operating systems. And the question is, what's the purpose of paging the page tables? And again, we kind of hinted at this a little bit, where our page table is so big that we need to page the page tables. And so when we page the page tables, what are the advantages? Okay, what does that do for us? We're spending this overhead. I think Hala had mentioned it earlier, that there's this time involved in paging, and when we're paging our page table, there's even more time involved to get from the logical address to the physical address. But why would we do that? What's the purpose? Why would we need to do that? Why would we want to do that? And that's what I'm asking you there. So again, you can see, if you go back to what I talked about at the very beginning, I'm looking for this higher level of thinking. Okay, once you understand what paging is, once you understand what a hierarchical page table is, and then you can start understanding why we would page our page tables and what advantages that gives us in an operating system. Okay, what does that do for us in our operating system? Okay, so we're looking at the situation where the page table gets to be so big that we need to page our page tables, and then if we page our page tables, what did we gain? That's basically what this is asking. And then the last homework problem, again, this gets back to this 32-bit logical address. We have a 4K page size, and we want to convert from this 32-bit address into the page number and the offset. Okay, your book says to use a 32-bit integer type. Java doesn't have a 32-bit integer type, and we're doing this code in Java. So just realize we're going to use a long, which is a 64-bit value in Java, and the actual address, this logical address that gets entered or gets passed to your routine, is going to just be stored in the rightmost 4 bytes, those 32 bits. Okay, the low order 32 bits. Okay, so your book said to use an unsigned integer. Java doesn't have one. We're going to use a long instead. But basically, all you need to do in this program, I gave you, I hope you all got that handout, where I gave you a test class and I gave you an address converter class, and all you really need to do is write the code for the address converter. And your book gives you some examples, and my test program gives you even more. So if we have an address of a virtual address of 19986, what's the page number? Okay, and your book says that'll be page number 4. How do you figure that out given this virtual address? And what is the offset? How far into that page number 4 do we need to go to get to this address in memory? Okay, 3062. Okay, so what this is basically saying is the virtual address here translates into page 4 offset 3602. And then my tester program just does a few more test cases just to make sure. I do 0 because I always try to test the limits whenever I'm testing a routine. So my smallest address could be 0. You can test to make sure your routine still works with your test case of 0. Here I test what is the largest offset that I can have, and the largest offset would be FFF, which is in hexadecimal, which would be 4096. So if I get an address of 4000, an offset of 4095. If I get an offset or an address of 4095, I know I'm in page 0 at the very last byte of that page. And if I get to address 4096, I'm in page 1, offset 0, because I'm in my second page. If you count the first one as 0, the second page is 1. And then if I go to kind of the biggest unsigned integer I can have in 32 bits, I end up with a page number of 1,408,575 with an offset of 4,095, which is giving me the last byte in my physical address space. Okay, so that's kind of what I'm looking for in this program. All you need to do is figure out how do you go from this number to these two, or this number to these two, or this number to these two, or this number to these two, and so forth. So the test program is going to test all these cases. Okay, it's a fairly simple program, and I gave you a good start on it. Any questions? Okay, I know you're getting hit with a lot of information, a lot of ways that things can be done, and the reason why your book goes through all this, and as you look through the different examples, because it does talk about how different operating systems do these different things, the thing is to understand operating systems, it is complicated, and there's so many different ways you can do something, and people are coming up with new ways all the time. So you kind of have to understand what the basics are, and what we're really hitting on here are really just the basics of how an operating system works. And to me, it still amazes me every time I think of my cell phone, and my cell phone does all this stuff. Well, it doesn't do swapping, we know that, but it does all this other stuff. And that's just amazing because I don't even think about it. It tells you how efficient our processes are and how efficient our memory is and so forth. Because, I'm just tapping on this and tapping on that, and it's just going along, and I'm not seeing that any of this is happening. And I take for granted that I can be playing music and I can be doing all these things on my phone at the same time. Yet the operating system is doing a lot of the things that we're talking about. So I just think that's pretty cool. Any questions? Okay, thank you for your patience. I know my voice wasn't very good, and I hope you were able to understand what I was saying. If you do come up with any questions as you're trying to work through the homework, feel free to email me. And other than that, have a good day, or have a good evening, I should say. Thank you. Thank you. I'm sure I'll feel better. I don't feel terrible. I just don't feel great. I have a little bit of a fever, and I have whatever's going on in my voice, and I'm coughing and whatever, but I don't think it's anything major. I think a little bit of rest and fluids, and I'll be doing better by the next time we talk. Okay? So have a good evening. I'll stop the recording now.